third quiz for Physics 201, chapters 5 and 6. Multiple choice. This was worth 3 points each, although actually I counted it as 25 points total, so there's an extra point factored in there. I have a box being pulled across a rough wood floor at a constant speed. What can you say about the work done by friction? All right, the friction is going to be negative, because if I have a box pulled in this direction, then the frictional force will be in this direction, and since the displacement is in this direction, they're opposite, and so that gives me negative work. How much work is required to stretch a spring 6 centimeters compared to 2 centimeters? That's a factor of 3 difference. Now the work required to stretch a spring is 1/2 kx squared, so if I increase this by a factor of 3, then that work, or the potential energy, is 9 times, because it's 3 squared, so the answer is D. A 1 kilogram block is traveling to the right at 3 meters per second. It collides with a stationary 2 kilogram block. And the two blocks stick together. I want to know what is their final velocity. Alright, this is a simple momentum problem, conservation of momentum. The initial momentum is just this block. That's going to be 1 kilogram times 3 meters per second. And that's going to equal the final momentum of this set of blocks, which is going to be 1 plus 2, or 3 kilograms. That's the mass of these two blocks combined, times VF. And VF then is equal to 1 meter per second. That is A for number 3. Which of these statements is true? Alright, is energy a scalar or vector? Is momentum a scalar or vector? Energy is a scalar, momentum is a vector. Let's see, that's A. Is number 4. Two boxes, one heavier than the other, are initially at rest on a horizontal frictionless surface. The same constant force acts on each one for exactly 1 second. Which box has more momentum? I know F equals delta P over delta T. They have the same force for the same amount of time, so their change in momentum is going to be the same. Both the same, so 5 is C. 75 kilogram diver swims off 500 kilogram raft. Diver speed immediately after leaving is 4 meters per second. What is the corresponding raft speed? So again, a simple conservation momentum problem. Initially, the momentum equals 0, jumps off with a certain velocity, 4 meters per second. So I want to know the velocity of the raft here. I'll call this VF1, this VF2. My mass here is 75. My mass here is 500. Alright, my initial momentum is 0. That means my final momentum is also going to be 0. That's going to be 500 times VF1 plus 75 times 4. Solve that for VF1. It's negative 500 over, what's 4 times 75? 300. Excuse me. Negative 300, that's this term, divided by 500, which is negative 0.6 meters per second. So VF1 is C, or excuse me, 6 is C. Which of these collisions is momentum conserved? Alright, momentum is conserved in all collisions. Whether it's people colliding, gas particles colliding, or cars colliding. Now, in particular, for gas particles, energy is also conserved. That's not what the question was asking. An elastic collision is one in which momentum and energy are conserved, like in the collision of gas particles. So that would be C for number 8. Alright, let's get on to the free response. This first one was a simple conservation momentum problem, at least a conservation of energy problem, at least the first part. I have this inclined plane. At first I consider it to be frictionless, and I want to know what is the speed at point A, which is halfway down. So that would be at a height equal to 1.5 meters. And then I want to know what is the speed at the bottom, point B. Alright, so I say my potential energy up here is equal to its maximum value, and my kinetic energy is 0. That's because the object is initially at rest. Here I have potential and kinetic energy. And down at the bottom, my potential energy equals 0, and my kinetic energy equals the max. Alright, so I will do part 1, A and B first. So to find the point halfway down, I'm going to say the potential energy at the top equals the potential energy at the halfway point plus the kinetic energy at the halfway point. Potential energy at the top is mgh equals mgh over 2 plus 1/2 mv squared. The masses cancel here. And say 10, 3 meters. So it's 15 divided by 1/2 square root. So the root of 30 I get 5.5 meters per second. Or let's see, keeping proper sig figs would just be 6 meters per second. So that's my velocity at the halfway point. I also want to know what is the velocity at the bottom. This is a little bit easier. It's part B of part 1. I'll start again. Potential energy at the top equals the kinetic energy at the bottom, because the potential energy at the bottom, since h equals 0, is also 0. So that's mgh, 1/2 mv squared. Masses cancel. I'm solving for v. It's the root of 2gh. H was 3 meters. That's the square root of 60. 7.7 or 8 meters per second. That is part 1b. Now let's look at part 2. Now I have a force that is described by this function, that the force is equal to negative 2x, means it's in the negative x direction, but it's proportional to x. So as x increases, then the force will increase. I'm going to take this to be x equals 0, and then it's going to go down here to x equals some final destination. And I want to integrate. In order to look at this first problem, I want to know how much work is done by the force. So for part 2, let's see, what can I do this? I'm going to sort of squeeze it in right here. So for part 2a, to find the work, I do the integral of f dx. That's going to be from 0 to my x final. I'll tell you what that is in just a second. F is equal to negative 2x. And the integral of that is x squared over 2, negative 2. So it's negative x squared. And I'm going from x equals 0 to x final. So that is going to be negative x final squared. All right, so that's going to be the work that's done by this force that's acting. And now I need to find out what is my final position. If this is x equals 0, well, you can find the length of this hypotenuse right here. If you're clever, you'll notice this is a 3, 4, 5 triangle. So it covers a total distance of 5 meters. Or you can use the Pythagorean theorem. That is the square root of 3 squared plus 4 squared equals 5 meters. And then so I take that integral, and I get it is negative 25 joules. That means that I'm taking away 25 joules of energy. So that's what the negative means. The work is taking away 25 joules of energy. So that was part A. The answer is 25. And I want to know what is the speed at the bottom of the plane. So I'll do part 2b right here. First, I want to know what is the total energy, and the total energy is equal to the potential energy at the top. That's going to be m times g times h. That is 10 kilograms times 10 meters per second squared times h, which was 3 meters. So 100, that's 300 joules. But then at the bottom, the energy is going to be 300 joules minus 25 joules. That's, I'll call that 275 for now. And then we'll return back to our proper sig figs. Excuse me. So that's 275 joules at the bottom. That's going to be my kinetic energy at the bottom. And then here I solve for V. So V equals 2 times 275 divided by m, which is 10, the square root of that. That's the root of 55, which is 7.4, or we'll call that 7 meters per second. All right, you might have gotten a slightly different answer depending upon how you rounded, but somewhere 7 to 7.4, maybe you might have even gotten up to 8, or, yeah, let's see, so 7 meters per second. All right, so that was part 2b, where you had to find the work done by this positionally dependent force, Fx equals negative 2x. All right, now consider this perfectly inelastic collision. What is the final velocity of the two particles? There's before the collision, and then after the collision, they stick together. So, see, I'll work it right here on the side. I know that my initial momentum equals my final momentum. My initial momentum is just mass times velocity, so that's 1 kilogram times 3I minus 2j, and plus 3 kilograms times negative 1I plus 2j. And then this is going to equal 4 kilograms times V final. I just want to know it in vector notation. Oh, the 4 kilograms just comes about because I'm combining this 1 kilogram and 3 kilogram mass. They're sticking together, so they'll have the same velocity in the end. And then I solve for VF. Let's just first distribute some of this stuff. So I get 3I minus 2j minus 3I plus 6j plus 4VF. Looks like our x component is going to cancel out, and I'm just left with 4j equals 4VF. So VF is equal to 1 meter per second in the j direction. So that's the answer. Alright, an object is initially at rest and has this mass. The object is acted on by a force over displacement. And then there, how much work is done by the force? This is simple dot product. I just say the work is equal to F dot D, 2I minus 3J, dotted with 4I plus 2J. I do FOIL, remembering that I dot I equals 1, J dot J equals 1, but I dot J and J dot I are both equal to 0. Remember that dot product is the same as I cosine theta. That is I dot I. So if that angle theta is 90 degrees, that cosine goes away to 0. So I'm just going to do my like terms. 2I times 4I is 8. Minus 3j times positive 2j is minus 6. So I combine these two terms, and then I combine those two terms. So that is 2 joules. So that's how much work is done by the force, 2 joules of work. In part B, I want to know what is the object's speed. Well, by the work energy theorem, I know that that work is going to change the kinetic energy of the object. And so 2 joules of work is going to equal 1/2 mv squared. See, I must have given you the mass up here. Yeah, the mass is 2 kilograms. So say 2 joules equals 1/2 of 2 kilograms v squared. This becomes a 1, 2 over 2, so v is equal to the square root of 1, which is 1 meter per second. That's part B. Part C is the x component of the force doing positive or negative work. Let's see, so what I intended there is that if you notice the x component of the force is positive and the displacement is positive. And if that's the case, they're both in the positive x direction, the force in the x direction and the displacement in the x direction. So that is positive work. But conversely, the y component, well, let's see, let me erase that so you can see it. The y component is negative. The y component of the force is negative, but the displacement is positive, so that means that it does negative work. Alright, that was number 11. There's one more. Okay, Alex throws a 0.15 kilogram rubber ball down on the floor. Ball speed just for impact is 7.5, and just after is 2.5 meters per second. The ball is in contact with the floor for 1 second. What is the magnitude of the average force applied by the floor on the ball? This was a homework problem. Hopefully you all got it. Intended to be simple. F is delta P over delta T. That's going to be mvf minus mvi divided by delta T. And then it's just a matter of putting in our numbers. We have to make sure we get the signs right for it to work out right. So it's going to be 0.15 kilograms. I'm going to go ahead and factor out that mass since it's common here and here. So I get 0.15 times Vf, which is 7.5 meters per second, minus Vi, which is negative 2.5 meters per second, divided by delta T, which is 0.01. Notice my ball is going down initially, 7.5 meters per second. So actually this should be a negative value. And then it comes down, it bounces back up, and it starts going up. So that should be a positive value. Sorry about that. And so that is going to give me a force that's going to be 0.15 times 10, negative 10, over 0.01. It's 1.5 over 0.01, which is what? 150 newtons. Negative 150 newtons. Now we need to think about this actually. I'm just asking for the magnitude, so I'm just looking for 150 newtons. But why does it come out negative? All right, this is the force. Actually, let's see. I think I had a mistake here. Oh, yes. I'm sorry. It does come out to 150, but it actually comes out to positive 150. I got my things here wrong. V final is, let me just go back and erase this. So this is where it always gets you on these problems. They seem simple, but you have to get your signs correct. My V final is positive 2.5 meters per second. See, that's just after impact is positive 2.5 minus a negative 7.5 meters per second. All right, so that gives me a positive there and there, and so it's going to be positive 10 and positive 150 newtons. So this is the force that is imparted onto the ball that causes it to change direction and to go up again. And obviously that force has to be pointed up, and it's actually 150 newtons in the upward direction. All right, sorry about that. Hopefully you didn't make the same mistake. That's the end. Or hopefully you caught it.